Oh, hello there. This is the second video in my new Formula Student series. Today we're going to be covering the schematics side of design in KiCad. Let's get right into it. So the first thing we want to do is create a new KiCad project. When you first open KiCad, it'll take you to this window where you can manage things to do with the project. So File, New Project. Find where you want to save it and give it a name. And you can see that creates a schematic file and a PCB file. Today we're just going to be looking at the schematic file. So to get started, select Schematic Editor, and this sheet that's created is where we're going to be putting all of our components to build up the circuit that we made in the previous video. What I'm going to do to make it easier is put this to one side and get up the schematic from the end of the last episode on the other side. So we should be able to just copy that onto KiCad, one component at a time. Of course, if you've sketched out a circuit on a piece of paper or something, you can follow the same steps. So the first thing I'm going to do is try and find every component on here and add them into the schematic. So we'll start with the chips and go from left to right. Let's look for the 4020. So to add a component, just click on here, Browse Symbol Libraries, and you can see, because it's the best, 4000 series is at the top, and we're looking for the 4020. There it is. Click on that, pop it in. It's the same as that. The only difference is that now we've got 12 volt and ground, 5 volt and ground, sorry. The cursor is now on Add Component mode, which is annoying, so right click, cancel. Then click on here again. We want the 4024 next, which unfortunately isn't here. But if we go to this, which is some more 4000 series chips, it is here. So we'll click on that. Next, let's look for the 74LS11. You can see 74's just below. 74LS11. Now, these are quite interesting when we add them. So you can see this is a 3-input AND gate, like what we have on the right. And when you click, you then have another one, and then this is power to the chip that contains those 3 AND gates. So for now, we'll just move the power out of the way. Next, we'll find the 4026. Oh no, they don't have it. So this is a situation that happens often on KiCad, which is that the included components, symbols or footprints, don't have what you want. So it's quite easy to import external footprints or symbols. I'm going to cover that in a future video, so to make sure you watch that, I'm going to blur out what I'm about to do. So now when I go in the component library, there's a section called Symbols which I've added, 4026, and that's what I want. There we go. We need 6 of those, so I'm just going to copy and paste them. Actually, I think we need 7, don't we, because I forgot to put a digit on last video. Next, let's find a 7-segment display. What I really want is a symbol that has pins A to G on the left, so I can just pop it right next to the 4026, because I was looking at the datasheet for the 4026 I have, and it doesn't actually require any resistors going to the display. So let's have a look for that. I imagine there'll be a display section, display character, and let's just go down and see what we can find. Ah, that looks good. Let's pop that in. You can see the pins line up nicely. What I'm going to do is drag it away slightly so that I think there should always be some green in between components just to make it clear that they're connected. And now I'm going to copy that for the other displays. Right, other components that we have on the circuit is the 4069 inverter, which they will definitely have because that's very common. 4069. This will do the same thing as the AND gate, so it'll add 6 of these and then the power to the chip. We only want 1 of them, so we'll use A, and the rest of them we'll throw away for now. It's fine to put stuff out of here, and if you've got a really big schematic you can change the size of this sheet, although there's a nicer way to do it with multiple sheets that link together, which I'll show in a future video. Now, it's not shown on the schematic from the previous video, but this 4 MHz input, we need an oscillator for that. So we can have a look for that. The oscillator that I have is in a 4-pin DIP8 package, which means the pins are numbered 1, 4, 5 and 8. So we want to try and find a symbol that has that numbering. There we go, 1, 4, 5, 8, DIP8, oscillator, perfect. Now I'll get the resistor for the reset button next. So resistors and capacitors and passive components, common semiconductors, they're in the device section. Device, you can see you've got C for capacitor, D for diode, etc. So we'll find R. We just want R, like that. And although there's no capacitors on the schematic on the right, we're going to add some to here, because there's a difference between a theoretical circuit, a simulated circuit, and when you actually build a circuit up in real life. So it's good practice to put what's called a decoupling capacitor across the power supply of every chip. So that's what we're going to do. So go up to C. So now I'll start thinking about the layout a bit more. You've probably seen that I keep deleting these and putting them back. That's because it's probably easier to just, seeing as these are all copied, just make one and then copy and paste it. So I'm going to do that again so that we can put in the decoupling. So with this capacitor, it doesn't have a value at the moment, and I want to set the value of this so that when we copy and paste it, the value gets copied. So to set the value, double click on the component, and then here it says value, type in 100N, 100 nanofarad. That's by far the most common capacitance for a decoupling capacitor. The other thing to set is the footprint. So if we double click on it again, footprint here, this is to tell KiCad what the footprint of the component is, whether it's through hole, whether it's surface mount, electrolytic, film. It doesn't know any of that. So click on the leaning books, and this is just like the symbol library except it's footprints instead. So this, we're going to use a surface mount capacitor, capacitor SMD, and the first capacitors that come up in this section are surface mount electrolytics, but if we scroll down a bit, we'll get to the standard small surface mount capacitors, and I'm going to be using 0603 because I have a lot of those. 0603 is realistically the smallest size you'll be able to hand solder, just in case you're thinking of making a board to solder. You can see how there's two numbers here, so often if I tell someone to use 0603, they'll select this top one. But the first size is imperial and the second size is metric. Imperial is probably more common. If someone says an 0603 resistor, the chances are they mean 0603 imperial, which is quite a lot larger than 0603 metric. That's just an important one to not get the wrong way around, because if you get a board with these, good luck soldering it. So just double click this to select it. Okay, and now the board knows exactly what this capacitor is. It knows what the value is and it knows what the footprint is. Any other ratings like the voltage, they don't affect the circuit board. Let's check the footprints for the other components as well. So the 4026, that doesn't have a footprint. The 4026 chip I'm going to be using is a DIP14, I think. No, sorry, a DIP16. So if we go to package, DIP, and we want DIP16, And then there's various different ones we can use. So we can put a socket there, which is probably what I'm going to do, so that the chips can then be removed in the future. There's also a wide version of dip. You've just got the standard one, which only affects the silk screen. That's if you're going to solder the chip straight in, but you might as well use sockets. Double click on that. Let's do the same for the display. So it already has a footprint assigned, but I know that footprint isn't correct for the displays I've ordered for this. So it looks like the display footprint that I need is this one at the bottom. So double click on that. Of course, if you're doing this project or a similar project, you'll have to know what components you're using and what footprints they need. So now I'm going to move the decoupling capacitor so that I can connect it. If you click on the end, any end with a circle, you can click on it and it will just start to draw a wire. So I want to connect that to power and ground like that. And then power and ground for the chip we can get by adding them. They're just symbols like everything else. If you scroll down to power with a lowercase p for some reason, then we can get 5 volt, pop that up here, and we can get ground, which we're going to put down there. Wire those in. I'm going to shift these up so that it looks a bit nicer. And this should be all that we need for one display, so I should be able to just copy and paste this. I'm going to bring this in slightly to free up a bit more space. Something I had pointed out to me recently, which is very helpful, is that when you're highlighting on KiCad, if you go from right to left, the only things that are selected are things that are entirely in the box you draw. Whereas if you go from left to right, it's anything that the box touches. So if you're trying to select a certain thing, just remember that. You can see with this capacitor, that's just the capacitor, but this gets the capacitor and the wires. So now I'm just going to copy and paste this back again, so we've got 7 displays along with their chips. Next I'm going to do the connections between each one that will carry the divided clock signal. So we're going to assume the top left digit is our least significant digit, so the input from the oscillator, once it's passed through our divider circuit, will go to this top left digit first. And just to make it match the schematic we made last time, it's going to go this one, then down to this one, then up to that one, down to that one, and so on. So we want the output Q10 to come down here, then go through that gap, and it's going to go to the clock input, which is here. Then we want the same thing here, Q10, it's going to go up. Every time you click when you're drawing a wire, it locks the straight line that isn't locked. It's very hard to explain, but basically, see this moves everywhere. If I click once, now the first one has locked in place, and I can make it longer, but I can't go shorter. That's now stuck there. If I click again, it's now locked that part. So every time you click, it sort of locks up to the next angle. That's a terrible explanation, I do apologise. What I'm going to do now, because I carefully laid these out so that they're all equally spaced, I should be able to highlight all of this wire and then just copy and paste that, like so. That will ensure it all matches, which keeps people like me happy. There we go, now they're all connected. Next, let's add the clock divider circuit, because that's going to take up quite a bit of space. Before that, I'm going to give myself a bit more space by making this sheet into an A4 sheet. So to do that, just go to File, Page Settings, and then you can just select A3 here. Okay, there, now we've got a lot more space to work with. As I said at the start, there are much nicer ways of doing this, but for this video I just want to get a circuit board as quick as possible. So just like the schematic from last episode, let's put it in the top right. We've got the 4020 here and the 4024 here. The first thing I'm going to do is give them both power, ground and a decoupling capacitor. So we can copy those from the 4026. There we go. Next, let's add the connections between them, along with the two AND gates that are required. So all I'm going to do for this is copy the schematic that we made last time. One difference you might notice is that the outputs on these two chips start from Q0, whereas on the software we did last time, they numbered them starting from Q1. That doesn't really matter, just take one off the pin on this one to match with the pin on this. If you're on the Formula Student team, I do have quite high standards for layout in terms of neatness and things. So, for example, these two wires that go to these pins, it would be frowned upon if they were done like this, so they crossed over. Complexity is fine, but unnecessary complexity is not good. Right, I think that looks okay to me. I'm going to move it right a bit now and add the oscillator. Again, the oscillator is going to have its own decoupling capacitor. This is probably the thing that needs it most because every time the output switches high and low, it can create some ripple on the power supply, and this capacitor helps massively with reducing that. Now all I need to do is connect the output of that to the input of the 4020, and that's our full clock circuit done. That will now create an output that has a period of exactly 1 microday. Next, let's add the extra bit of circuitry required for the final digit, the most significant digit, the days counter, to reset it when it reaches 7 so that we don't have more than 7 days in a week. So let's bring down the inverter that we need and the final AND gate. And we need to get to the output B, so I'm going to drag this away a bit for now. I'll bring it closer once we're done. Click on this, add a wire, because with these there's a circle and the circle automatically selects the add a wire pin tool. But here there isn't one, so add a wire, click on here, I'm going to bring it down, and this wants to go to the AND gate, so let's just end it there for now. Bring the AND gate up. Now we need to put our inverter in after the Q10 output. I'm going to move all of this to behind the display just for neatness. And now just feed the output of this AND gate to the reset pin of that digit. That should be all that we need. Something I've just spotted that I forgot to add is the cathode of the displays. What we want to do is join the two of these pins together. They're already connected on the display, but there's no reason to not also connect them on the PCB. Then we're going to add a ground to that. These are common cathode displays, so if you're using common anode displays, then there's two things you should know. First is that common anode, the common pin you connect to positive instead of negative rail, and secondly, it won't work with this project because unless you can find a special version of the 4026 or you invert every output, the 4026 is designed to drive common cathode displays, which unfortunately seem to be quite a lot harder to find. I had to buy some specially for this. So now I'm going to copy and paste this onto all of them. Of course, if you're following along, do this at the start and then you don't have to do it now. Something else I've just thought of that you might be tempted to do for example here, is if you have a ground, rotate it and then put it there. Never rotate power supply symbols, just because the way that people know this is ground is because it's pointing down, a bit like it's pointing at the ground. So if you point it up, then no one is going to know. People will probably think it's a supply. And although it's labelled, the key thing to go for with a schematic, as long as it works, after that you want it to be clear. So clarity is the thing to prioritise when making a schematic. The next thing to do is deal with all of the weird leftover bits. So the power to the two chips we're using is quite easy to deal with, the same as all the other chips: decoupling, capacitor, 5 volt and ground. I've just remembered we also need to assign the footprints to these two chips, so you can do that by clicking on you can click on any of the AND gates or the power supply for them. I'm going to just do the power supplies because it's easier. That will change it for the whole thing. It's one footprint that's associated with multiple symbols, which is quite unusual. That probably most common scenario where that will happen is simple jelly bean logic chips like these. So again, we want dip, and looks like these are both 14 pin. So we'll go to package dip 14 socket. And I've also remembered we haven't done the footprint for the oscillator, so let's do that. It does come with one, but I'm not sure whether I want to solder the oscillator straight into the board or whether to put that in a socket too. I think the oscillator I want to use has very short pins that pop out of a socket, so I will solder it straight in actually. I will leave that as it is. Next, let's get the 5 inverters that we're not using and put them in a nice order. And what I want to do is ground every pin, because sometimes, especially with high-speed chips, if you've got something like an input, digital input, if it's floating, you can get noise on it and then oscillations. So for example, the output of this inverter is pin 12 and the input is pin 13, so they're right next to each other. You could get a bit of noise on 13 that makes 12 go high, which then creates a little bit of interference or noise and couples back into pin 13. And if you connect the input and the output of an oscillator, of an inverter, then you'll get an oscillator, and we don't want that. That can lead to quite high power draws. So I've had a high-speed version of the 4069 before, just on a breadboard. Plug it in. If all the inputs are grounded, it draws 0 current, as it should, as in less than a milliamp. If you leave all the inputs floating, you can have this chip just on its own on the breadboard drawing 20 or 30 milliamps, because every inverter is oscillating as fast as it can at many megahertz, and we don't want that. So let's ground all of the inputs. And the outputs they're not going to be floating, because we're driving the inputs low, the outputs will be driven high. But we're going to do this on more pins later on, but I will start doing it here. What we're going to do is use this, add a no connection flag. And that just makes it clear to KiCad and anybody looking at this schematic that those pins aren't connected to anything. And I'll pop these out the way over here for now. The next thing to add is the reset system. So I'm going to start by joining all of the reset pins together. And next I'm going to add the pull down resistor. So this is going to keep the reset pins low, which will stop the chips from resetting, unless I press the button, whose symbol I forgot to add. So now let's find that. So there should be, I think button will probably be in switch, so S. You can search for things if you click on this, but it's more fun to find them. I recommend exploring many menus and things just to see what you can find. Switch. And we just want a push switch like that. Normally open. Connect that, and that is going to go up to 5 volts. We need to give this resistor a footprint and a value, so we'll do the footprint first. Exactly the same as the capacitor, even the same numbers. I'm going to make this a through-hole resistor though, so that when soldering I can demonstrate different techniques. So resistor through-hole. These are your standard resistors. You've got different lengths, different diameters, things like that. So I'm going to go for this one. I think it looks nicest. And the value, we're going to go for 10k. So for non-critical components like decoupling capacitors, well, they're critical components, but the values aren't too critical. Especially if you're on the Formula Student team, you want to try and stick to standard values as much as possible. So for capacitors, it might be 100 nanofarads, 1 microfarad, 10 microfarad, 100 microfarad. Resistors, you've got 1k, 10k in particular. 10k and 100 nano are by far the best values to use if it's not too important. So for a pull up or a pull down, I would always recommend 10k unless a data sheet or something else specifies otherwise. That's useful for reducing what's called the BOM, the bill of materials. So actually you can see it mentioned here, bill of materials. If you've got a circuit with 1,000 resistors on it, if you've got 100 different values and 10 of each, that's going to cost a lot more to buy than 1,000 of one value, which realistically you're not going to be able to achieve. But for example, if you had 47k, 100k and 220k on the board, just have a think about, can you make them all into 100k? Will it actually affect the circuit? So there's not too much left to do. The one thing I did realise I also forgot to do is the display enable and clock enable pins need tying high and low. So I'm going to see if I can squeeze that in. I might have to drag the digits apart a bit. So it looks like I can fit that in. I'll just drag this capacitor up so that the text isn't overlapping. And then I can hold shift to select both of them, copy, paste. And the way the software sees 5 volt and ground is they're just labels. So you'll be familiar with labels if you've used LT Spice or potentially quite a lot of other software. So you can actually add custom labels on here by clicking on this. So I can say hello, and then I can pop that on there. And now every wire, every connection that I label with hello will be joined together. It's the same with this, so all the grounds are just joined together, all the 5 volts are joined together. If you're making a big board or even a simple board like this, labels are very good to make it a lot clearer what's happening and declutter everything. So in a future video when I go over how to actually make this look nice, labels will be one of the things we'll take advantage of. Now the next thing to do is connect the signal from the clock divider to the input of the least significant digit. So it looks like the output is this line, so I should just be able to go out and up like that. And I'm going to do, you might remember me saying the no connection flag, so I was going to add some more. So I'm going to add that to every pin that isn't connected, except this AND gate, because I'll get back to that. We're going to connect that next. Perfect. Right. What I was going to say with this is the AND gate, we can't leave the input floating, because then if it floats its way down to ground, the AND gate won't output high, even when the two inputs we care about are high. So what we're going to do is connect that input to 5 volts so that it's always high. And that should be everything we need. Hello, Fred from the future here. Just realised that I forgot to add in the power connector, so I'm going to quickly do that now. The board runs on 5 volts, so I'm going to just use a USB connector. My favourite is type B, because the sort of square one, because I've got quite a few of those connectors, leads, and they're very mechanically robust, unlike new versions like USB-C. So if I scroll down in the connector section, we should have USB-B, there we go. And let's just pop it there. And then it's quite simple, basically 5V connects to V-bus, ground, and this is true if you're using micro USB or anything else as well. Ground goes to ground. Data lines, we're not doing anything fancy, so we're just going to leave those floating. Sometimes some devices like them shorted or connected with a certain resistance, but it doesn't really matter for something like this that's not drawing much power. And if you are drawing a lot of power, it's probably worth having a chip on it that'll negotiate that with the host device. I would ground the shield, but I've been told not to by somebody, so we'll just leave the shield floating. And that is it really. Got to give it a footprint as well, actually, so let's find that. There should be connector section somewhere. Connector underscore USB, there we go. USB-B, and there's a few built-in ones. The one I have is this, so I'll just go for that. Right, I'll return back to past Fred. Oh no, you won't. This is even futurer Fred here with two other little things I've remembered. The first thing is a fat decoupling capacitor on the input from the USB, and I think this is actually going to be 100 microfarads, which is quite a lot. 100 microfarads, and it's a surface mount electrolytic. It's 6.3 by 5.9. There we go. And the other thing I needed to add, which is very important, is the decimal point on the day digit needs to be on, because we've got millidays and microdays. It's going to be, if it's Monday, it's going to be 0.5 would be midday on Monday. So we need to make sure that point is on. So for that, we're just going to add a resistor and tie it up to 5V. I'm not completely sure what resistance to go for so that it's similar brightness to all of the digits, because the outputs of the 4026 aren't a specific resistance. They're more just sort of whatever current they end up being. So I think I'm probably going to go for 1k ohm. It doesn't really matter if it's a bit dim. I can also change it if I need to. And this resistor is not going to be through hole, it's going to be surface mount, good old 0603. So resistor surface mount 0603. There we go. Right, hopefully that is now it. I'll return to past Fred. If there's anything I've forgotten, I'll mention it in the next video. And what we're going to do in the next video is do the actual circuit board for it. So now that KiCad knows all the components we're using, how they're connected, and what footprints they have, the next step is to tell KiCad how big our board's going to be, then lay out all our components, and then connect them all together with tracers, which is probably the most fun part. We even get a nice 3D model at the end. So thank you for watching. Apologies for the delay from the last video. Hopefully the next one will be in a day or two, and goodbye.